OPCDI presentation. And today, I'm a quick introduction about myself. I'm Melvin Francis, and I'm working with BE Services, and I take care of the OPCA plus TSN related projects. And today, I will be presenting along with my colleague Roland from Pack Automation. So he has been part of this activity, and they are our end consumers who are using our research outcome into their products and their projects as well. So let me start the presentation. Yeah, here we go. I hope my presentation is visible. So when we started this research activity back in 2020, we started to apply for grants. So what drove us to start this project was we saw the scope for improvement in the current Ethernet protocols. So what were the gaps where every protocol is vendor dependent and there is lack of interoperability, and you need a custom hardware development for deterministic Ethernet deterministic purposes or for high speed cycle time. And then for different protocols are needed to transfer a single byte of data from your factory floor to the cloud. And you need separate network assets for IT, and you need separate network assets for OT, which increases the cabling cost, or it increases the maintenance, and it's a overall mess. And also when you want to transfer the data, you need a handover, and there is a lot of security concerns. And these were the regular problems in the legacy Ethernet protocols. So the challenges and adding pops up part 14 to the OPCA specification made it easy for using OPCA even for high-speed communication and deterministic Ethernet purposes. So everybody knows OPCA TSN is the solution, and it's a futuristic option to go for. But what are the challenges were to select a stack of from an exhausting list of providers? Small footprint is always a concern. Getting a small memory footprint is always a concern, and integration efforts of OPCA and TSN as combining them together is always a new effort for a new hardware, and development of TSN stack and supporting modules was a challenge, and testing ecosystem itself, which is quite expensive and it's not easily accessible. So seeing these challenges, we went for a grant, and this was the SDK architecture that we promised. So which is also as specified in the UAFX specification. We can see that on the lower level layers, we would need LLDP, we need .1AS, QBV, we need a TCP/IP stack, and also to orchestrate all this, we need an RTOS to do it, and combined together, we need security. So when we talk about OPCA TSN, it's not just two keywords, but there is a bunch of stacks that needs to work in harmony to achieve this. And also they should be in low end footprint so that they can also be used in small devices up to the sensor or drives level. So we came up with this approach, and we applied, and we started this research project in May 2022. So we won the grant, and then we kickstarted the project, and system specification was defined. And in March 2023, we presented our initial prototype at Embedded World. And the PTP stack was developed in September, and in November 2023, and last SPS, we showed the prototype that we will be seeing right now. And so December 2024 will be our a final publication of our results and outcome of this research activity. So OPCUAFX connectivity itself provides a lot of options for communication. So depending upon our necessity and the network requirements, we can choose the various options that are available. And today's presentation, we are specifically going to see how UAFX can be used in the industry factory floor, which is specifically controller to controller and controller to device. So yeah, so these are the two parts that we are going to see in our presentation today. So I have my colleague Roland, who will be presenting like how UAFX was useful for his use case in his factory floor, like for creating packaging machines. So he will be explaining further from now. Yeah, yes, Roland.
Yeah, thanks a lot, Melvin. Can we come to the next slide? So from end user perspective, we chose OPCUA from the beginning as a standard protocol for communication between our PLCs and HMIs or some process observer solutions. But C2C was new to us. So Melvin and BE services introduced us to these topics, and together we defined some benefits. For us, the core concept features our modular thinking inside our machine concept. So C2C gives us more options in terms of a less static network architecture. So when we design our machines, we think in modules that can interact between each other and against something like we call process orchestration layer. All these modules are not static as we implement them. So during commissioning, for example, we add one by one by one. So that is a drawback in the current implementation with real-time network systems with C2C communication. It's like inbuilt feature. Second, the OPCUA SDK, which is open source, we heard from Fraunhofer, was a great option for us to implement our own solutions, and this in a minimum time. So there was no need to purchase any vendor SDK. We worked with the open source stack, and it worked perfect from the beginning. The third option, or what we had in as a benefit, was freedom in design of our application components. And now we can talk about the application we used it for. We designed the robot to controller communication in 3 steps. So first of all, we designed a virtual robot on our PLC platform. We do all the path planning and stuff on this robot, and we just publish the set positions for the individual axis. During our first trials and commissioning phase, we did it virtually. So the PLC published position information, and there was an IPC consuming this information and render it to a 3D model. So one component in the network consuming this information. And in the second go, we added the real system, and now it was just out-of-the-box functionality. The real robot consumed the set positions from the PLC, the path planning, and feedback the information about status of the axis and stuff. And as a third option that we added later on in the project was a observer instance that just monitors set pos and feedback position of the robot to give us as developer the information we need about accuracy of the system, about behavior, internal behavior, reaction time, and these information that we need to evaluate our system and its performance. And all these inbuilt in the C2C communication, just step by step, without the need to change any of the controller or subscriber hardware. And in the final design, we showed that the automation last year, we did the following approach. So there was a BNR PLC doing all the... next slide, please. Yeah, we did the path planning on the PLC. You see in the background that the video stream on the right-hand side, the APC 2200, standard APC hardware from BNR. We set up the virtual robot, and we communicated the set positions during the TSN switch, and the subscriber was a neural robot with the implementation from B services, the TSN stack or the ETSN stack. In parallel, you see there is a real-time communication power link, so the standard BNR bus, but that was just for our purpose during commissioning. We needed something to reset communication, for example, to reset and activate the safety features of the system. So there is some standard communication in parallel, but that's current work we do to get rid of these communications. So we try to set a server client structure besides the TSN stack to communicate information that is relevant while booting both systems to get them in sync, for example. In the end, this approach worked. You can see it on the right. The robot followed the path we planned on the virtual side, which we can explain briefly via the next slide, how this approach was built. So we have a real hardware that is the left-hand side. We have 6 axes working, or that are implemented in the robot PLC. So there is a loop, a cyclic communication. There is its own protocol. On the right-hand side, we have the virtual robot. So we designed the system more or less like cyber-physical approach. So there's a real world, there's a virtual world, and they interact. So the real robot, the real axis publish their actual position. The virtual system subscribes to them, does the path planning, so produces set position, calculates set positions from the actual position of the robot, calculates offsets, and calculates the set pos for the next cycle, which we had 1 millisecond as our target cycle time. The logic PLC, the virtual robot, publishes this position, the subscriber on the real robot, and works with them, writes these positions to their axis, and so we close the loop. The target of 1MS, we did some round trip testing. Melvin gonna explain. I want just to highlight one more benefit of this approach. As all the OPC idea, I think it's independent, vendor independent. We did the same approach here. Any vendor that implements such a subscriber publisher mechanisms can be controlled remotely by our virtual system. So that is something we research on and are in communication with different vendors on robot end. How to implement a, let's say, open interface that allows us as machine builders, as special machine manufacturer in the end, to just implement our PLC code once with the ability to remote control a variety of vendors. And I think from our end user perspective, OPCUA and the foundation is the core principle we're gonna set our bet on. Melvin, let's see the round trip examples.
Yeah. For the round trip time to get our the target of 1MS came out from the commands that we need to send from the PLC to the robot. This was needed at 1MS cycle time round trip, but we were able to achieve the round trip time of 2x the cycle time. So every time we send a packet from APC, so imagine you are sending 1 byte of data, so it comes through the TSN switch and then it goes to the robot controller, gets looped back, and then to receive it back on the BNR APC controller, it takes the round trip time is 2 times the cycle time. So every 2ms you receive the packet back. So the overall the closed loop cycle is 2ms, and we were able to achieve this using the regular TSN patches that are provided by the Linux kernel itself. So once we had the performance required for the robot achieved, so we were able to control with the same mechanism that Roland explained now. So the one great thing about OPCA is that, so since you can see that all the APC, the robot from Neura, so everybody are running OPCA here. So this gives us an easy access to monitor all the variables that are used to control the robot. So robot or the sensor values from the robot, or also the control data or whatever we want to monitor from these devices can be easily accessed using an external client like an edge AIoT device. And then it will help you to push the data to the cloud securely and easily and without any other protocols. You can just send your data from the factory floor to the cloud with the same namespace, and it becomes easy for you to plot the graph. So these are the exhaustive list of sensor to cloud use cases. So you can see the collection of machine and process data, which was once a cumbersome task, becomes easy, and secure data of between OT and IT becomes possible, and secure automation, secure access to your automation systems, and also software updates since you are having an OPCA server running in all these cases. So these kind of new additional use cases becomes an easy possibility without having any additional firmware to do it. And remote monitoring of key machine information in a customized dashboard. So just like how we saw on the previous slide, and also the local treatment of data versus third-party cloud systems. So once you have your data collected, so some companies are reluctant to push their data outside of their company. So to have everything collected on your in your premises and doing the edge analysis becomes an easy option. And also, as we know already, remote maintenance and firmware updates becomes easy. So this is everything without AI. And also once you want to incorporate your AI models, so once you have the data, so it gives you door to anomaly detection, predictive analysis, and quality control. So right now we have one use case where we detect the anomalies, where we have implemented OPCA server and publish subscribe kind of system for one of the machines. So this is a palletizing machine, and every time it picks up, it drops some load of the palletizing machine. So our models were able to detect when this particular anomaly happens, and we provided this data to the machine builder, and it helped them to make their machines more efficient and how to reduce these errors. So these are some of the use cases that we were able to achieve because you have implemented UAFX over the other legacy Ethernet protocols. So our next steps are to achieve the controller to device. So this particular specification is still in progress, but we have already done some prototypes here. So as you can see a Linux controller here sending the position commands to a drive, two drives that are on the device layer. So you can see the two drives which are based on Renesas controllers, TSN controllers, and they are able to move to the position that is being sent by the Linux controller from here. So this is for target towards achieving a low footprint platform. And right now, until now, our overall memory footprint is closing to 560 KB of memory, and we are proceeding to reduce further as well. So 560 KB of RAM memory was the amount of memory consumed to achieve this solution. And so these are the supported reference designs for now in this research project. So Renesas RZ-T2M, which we consider as the lowest platform, and then we have AM64X Sitara from TI. So this is like a dual processor design. So this is for bigger applications, and then finally it's from the Linux box configuration along with Intel i210 NIC card kind of configurations, which can range from Atom processor to even i5 or i7 PC as per your requirement. So our future work in this project would be wireless TSN, testbed construction, creating reference designs and field testing will be our future work. So we will be presenting our releases in upcoming SPS. So this is the overall progress that we have achieved in the project. And thank you so much for listening. And sorry for the initial glitch, but hope this presentation was helpful and you have some takeaways at the end of this presentation. Thank you so much for your patience.